Good afternoon to one and all, to all the participants. So this is the last and final day, day 6 of our 6-day online faculty development program, sponsored by Atal for the Department of EEE of KLNCE on the topic IoT and cyber security in power systems. So today we'll be having 3 sessions. First session will be handled by Engineer M.A. Vignesh Sir. He's an assistant engineer at Support Dispatch Center in Madurai. So before getting into the session, I'll just have a small introduction about the speaker of this session. So Engineer M.A. Vignesh Sir, he is also one of the renowned alumni of our EEE of KLN College of Engineering. He has completed his BE in 2010 and he has completed his ME in Energy Engineering in 2013 from BSG College of Technology, Coimbatore. And he joined in AFCONS as an electrical engineer and he has worked there for the 4 years. After which he has cleared a AE exam and he has joined as an assistant engineer in Tamil Nadu Electricity Board in the year 2017. And he's been working in this subload dispatch center for the past 5 years. Vignesh sir, so he's going to deliver a session on the topic power system security in smart grid. Sir, session is over to you, sir.
Very thank you. Good afternoon for everyone here. I will share my slide right now. Hello. Everyone is able to view my slide, right?
Yes, sir. It's visible, sir. Can I go with full screen mode, sir?
Yes. Yeah, is it visible?
It's visible.
Yes. Okay. See, I am Vignesh. I'm working as an assistant engineer in Subload Dispatch Center. For the past 5 years, I've been working here. I will share my knowledge and how we are maintaining the grid smoothly. I will share all my knowledges in this slide. Okay. First, initially, we are going to concentrate only on this distribution, transmission side. Okay. Because all of our main form of energy transfer is only transmission, right? From generation to distribution, we have a main part of transmission lines. Okay. These things, you know, before independence, we had small isolated systems. Okay. Next, after 60s, we had generation and transmission by state electricity boards. They were starting as a small isolated systems. Next, after 60s, they started interconnecting systems between neighbor states. Okay. Next, it emerged as central sectors. They formed a NTPC, NHPC, and your NTPC, all your thermal power stations were formed. And planning for generation and transmission on regional basis was also taken place. Later in 80s, they started to integrate through 400 kV substations. Okay. The central government started generation utilities. After that, they started to share with the state also. And they formed this regional grid so that they can connect between states. In 80s, they started to just make the grid so strong. Okay. First scope was they just want to interlink all networks, because some area we had a more power scope of generation, and other area we had more load centers. So that in order to just connect them, we just started this interconnecting regions. In 1989, Power Grid was formed to give thrust to implementation of transmission system associated central generation stations only. Later, inter-regional links were also planned and developed to facilitate exchange among various regions. Okay. And during that time, resource planning as well as grid operation, only operation frequencies of various regions continue to be regional specific. Initially, Tamil Nadu had a frequency which northern states didn't have, and everyone were having their own frequencies, and they were operating independently. Later, after Power Grid integrated everything, we just came into a single one grid system. That is why they focus for national grid. Focus of planning, generation, transmission system shifting from orientation of regional self-sufficient to the concept of optimization utilization of resource of all Indian state to transfer power from surplus region to deficit region, utilizing maximum resource from diversified regions and ensure reliable economic and power quality. We have formed this national grid. Okay. Next, we formed the Ministry of Power after independence. This work of Ministry of Power is to frame policies, process the implementation of new project, enactment of legislation issues in regarding to power generation, transmission, and distribution. And this Power Grid Corporation of India Limited was formed to transmit power, and for planning of transmission line between regions, they just started this. Next is Central Electricity Authority, CEA. Their work is to advise Ministry of Power and policy and formulation of short-term and long-term power requirement. They will just give advice, and with this recommendation, Ministry of Power will frame policies. Again, every state and every central has its own regulatory commission. This regulatory commission is a central and state regulatory commission, or they just decide the tariff. I mean, they regulate the tariff. You have to give subsidies, or what rate you have to just fix the charges for your consumption. Everything will be decided by central and state regulatory commissions. Okay. See, this is this initially we had 5 regions. One is north region, west, east, northeast, and south. These 5 regions operated very independently. Means that they didn't have any link, and there was no inter-transmission lines also. They were all independent. Then what Power Grid did this in the year 1991, they just integrated this east and northeast region. Later, in March 2003, they started to integrate east and northeast. Okay, sorry, west and northeast. Everything was like this. Fully they just covered. In the year August 2006, they just integrated the entire north.
Vignesh sir, sorry to interrupt, sir. I think your slide is not moving, sir. I think so. Actually, we are able to see only the front slide, sir.
Oh. Just a minute.
Yes, sir. Now it's moving, sir. Yeah.
Now it is okay. Can I keep it
yes,
like
sir.
this?
You're able to see a site called Human Body and Power Systems and an Indian map, sir. Yeah.
Okay. Means that see. Now you are able to
moving, sir. Yeah.
See, initially all our regions were like this: north, west, east, south, and northeast. Okay. Later, after Power Grid came, they just first interlinked east and northeast. These two states they interlinked. Later, they interlinked with in March 2003. Entire west along with the northeast they have interlinked. In August 2006, they just integrated all the northern states. Okay, completely. In 2014, they integrated the entire grid. Now they had only one frequency, that is 50.00. Even now they are following everything as a single unit, and we have one India, one frequency system. See, the frequency, just a human analogy. Voltage is like blood pressure, and frequency is like heartbeat. Okay, you have 50 seconds for frequency and 72 beats per minute. Okay, if your generation and load mismatches, you always get similar to this. And if your frequency is deviating, your heartbeat will deviate. This is just an analogy for how our system works. Next, we have our. I'm working in subload dispatch center. We have our state load dispatch center. Above that, we have regional level dispatch centers, and above that, we have national dispatch center, which is where they monitor all the states, all the 33 states. Dispatch center will be monitored by NLDC. They just decide whether what is the. I mean, they will just monitor if any abnormal is happening. They will just act immediately. Okay. Current at present, this is the data which is available at in National Load Dispatch Center. Now at present we have a 410 gigawatt of installed capacity, and at our peak load, our we have a shortage of 0.5%, and our per capita consumption is 1,255 kilowatts. Our plant load factors is around the 63%, and our aggregate transmission, aggregate this is ATC losses is around 17%, is national average. Okay, next, this is a layout of our present grid. We have to manage bulk generation, transmission, distribution, customers, market, operation, and service provider. Here in this grid, we are working in this operation area where we will manage everyone. Okay. For a grid operator, there are two important factors for operating system operations. Okay. One is economical operation of power system. Next is power system security. These two things are very important. For economical operation, we follow some procedures. For power system security also, we have some automations. Okay. For economical operation, power scheduling and forecasting of the grid is the most important part of economical operation. See, we have to forecast what is going to be we have to at least predict what is going to be our load or what we can generate. Everything we have to see. Load we can predict. We have to forecast. For generation, we will be knowing. We know how many generators we have. In Thoothukudi, we have nearly 1,010 megawatt of TTPS. In North Chennai Power Station, we have another 1,200. In MTPS, we have another 1,600. We have Kudangulam, which is where our central government contribution is around 1,000 megawatt. With this, we will schedule. Okay, what is generation we can make, and what will be the demand we will predict. Okay, we have two things in this. One is day ahead schedule, means that a day before itself we will schedule what is tomorrow's demand, what it is going to be. That is, we will, according to the demand, we will schedule the generation one day before. Okay, in real time also we will schedule. Real time scheduling happens when, suppose when we have a generator, it goes into outage. We have to match the demand with the other generators. That is real time scheduling. Okay, see, day ahead schedule. In day ahead schedule, we have thermal power plants, renewable energy resources, and we have this long-term open access, medium-term open access, short-term open access. These open access, they have agreement with our ACBs, our state electricity boards, where long-term, if you have an agreement with our state board, state electricity board, like more than 3 years, they will go under long-term. I mean, with after more than 1 year and between less than 3 years, now you will have 2 years. You have a medium-term open access agreement, and if it is less than 1 year, it will go under short-term open access agreement. In everything, all those generators have to schedule their generation well before one day itself, so that we will be knowing how much we can schedule for the next day. And we have hydropower plants. We have hydropower plant. We have Periyar. We have Kodayar. We have Surliyar. We have Pavnasam. We have many things. And for gas power station, we have this Valudur VGTPS. I think you know VGTPS. We have Koil Kalapal gas thermal power station, and we have other central government shares also, like nuclear thermal. We have joint venture with the NTPC. We have nuclear power corporation with the NCCL also. We have agreements. Through this, we will know how much we can generate well before 24 hours itself. We will just combining all these production. We will forecast the generation. Generation forecasting will be done for next 24 hours with 96 blocks. Here, what we will do is we will each block each hour we will convert into 4 blocks, so that every day we will have 96 blocks. For this 96 blocks, we will continuously schedule generation well before 24 hours. Okay. Let us consider the generation as a P generation. Okay. Next, after using, now we are using an AI predicted demand forecaster technique, where we will consider previous year record, next whether it is a Sunday or holiday, or what demand yesterday it had, regard with this all, we have a AI generated. We have right now purchased a thing. Where with that, previous also it was like that. We will forecast weather condition, everything. With that, we will predict demand and optimize energy needed for the next 96 laws. We will consider this as a P demand. Okay, we will have we know generation, we know what is the generation, and we will predict. We will predict the demand for next day. Then this P schedule will be given by NLDC. Okay. See, if suppose the demand is not matching with the generation, this excess, excess load, excess generation will be supplied by NLDC, will be scheduled by NLDC only on availability basis, or we can purchase this in open market. P excess can be scheduled in a real-time market, like we have Power Exchange India Limited and Indian Energy Exchanges and Hindustan Power Exchange. We have only 3 exchanges like our for equity market, we have our NSE and BSE. Similarly, for power market, we have these 3 exchanges where when suppose if TTPS is stripping, TTPS has 5 units out. If suppose 1 unit is stripping, it is around 210 megawatt. If it is stripping now, it real time, we will not be in a condition to meet the demand. That time we can just purchase automatically from this real time market. Okay. It is like that. Our demand from our side, which we have predicted, as earlier said, which we have predicted, we will submit it to regional load dispatch centers. Okay, this regional load dispatch center will again submit to NLDC. This NLDC, this is the NLDC nothing but they are a subsidy of this power grid. Everyone, all the central government PSUs will have a link with this. They have more than 45,000 megawatt of thermal generation, so that they can schedule. With this demand, they will give us a schedule. They will give some megawatt. You can just take for some 4,000, 5,000 megawatt from the grid through interstate feeders. They will just give say us. Means that they will give a schedule of megawatt which you can take from the grid. Okay, we know what our generation is. They will give some through interstate. They will just give some generation to this. Suppose if it is not meeting with the demand, this excess amount we will buy in real time. Real time, they may suppose if available with the NLDC, if the power is available with the NLDC, they will give us. If not, so we have to go for a real time market where I said all those exchanges you have to buy this. Through this, we have to economically operate the grid. This suppose if you know what will happen in real time. If NLDC is giving a unit price for 3 rupees or 4 rupees, if you go for real time, you will feel that it will real time market per unit generation will cost for 8 rupees, minimum 8 to 16 rupees during peak time. Okay, that is why forecasting demand is very important. It is very important for the economical operation of the grid. If suppose if we buy in a peak time for 16 rupees per unit, but we are charging consumer for a lesser rate, but we are buying it for a higher rate, it will be like that. So automatically we will end up with the loss, which will be again paid by the taxpayer of this our state. Okay, so it is proper for economical operation. In grid point of view, we have to schedule generation and we have to predict demand very properly. If there is a mismatch between these two, again we will end up with the losses. This is economic operation. Coming to security point of view, see again this slide. Okay, this is a slide where real time I'm showing. It is not in real time. This is how we will see our monitor. See, now the frequency is 49.95. Our demand is something around 12,941. See, this is this schedule, which this will be scheduled by NLDCs. Right now they have given 8389. This schedule plus our generation is different. Okay, this schedule plus our generation should demand this meet. Should meet our demand. If it is not meeting, again here you can see how much we are drawing interstate. 8617 is what we are drawing actually, but 8389 is what we are supposed to draw. Means that we are overdrawing now. We are just overdrawing 228 right now. This 228, we are having a separate team in the back end. They will purchase it from the open market, real-time market. If NLDC is having it, they will just provide us. If not, so we have to purchase it in the real time. These things, if back end, they will take care. But for grid operation, you can see whether what is the situation of the grid. Suppose now the frequency is good. It is around 49.95. Suppose in worst case, if frequency is dropping, something around 49.85, na, if your deviation is higher, in real time market, if you go and see your, your price of unit will be very higher. If you go and buy that time, they will be benefited a large time. They will be benefited a large. Okay, this is for optimal, our economic operation. Next, we will go for a security. As a grid operator, we need to just monitor the entire grid, and suppose emergency or any corrective action has to be taken, then and there we have to act. Okay. Power system security practice suitable design to keep the system operation even when electrical components fail. Suppose any abnormalities happen, we have to act. Okay. Power system securities can be said to comprise of three major functions. We have three major functions that are carried out in energy control centers. What I'm doing. Okay. This first we should monitor the system. We all know monitoring is the first thing. Next, if any, we will just analyze any contingency is there, whether frequency is dropping or voltage is rising. Everything we will analyze. Suppose if it is correcting, it is going to a extent we have to take corrective action. Now we will take actions. Okay. For system monitoring purpose, we use SCADAs. Okay, all you know, these all workshop you would have seen all these things. SCADA for communication. Now at present we are using SCADA for our communication purpose. SCADA is responsible. SCADA is like our sensors. Power system is human body. SCADA is like our sensors. Okay. In system components, in field level, we'll have CT and CVTs. They are the main things. They will supply input to transducer. This transducer again will give analog output, which will be fed into RTUs. This again, RTUs will have an ADC, analog to digital converters, and this RTUs will again convert and transmit through communication channels. In communication channels, we are using OPGW and PLCC communication. Both we are using, but we are not into VSAT or GSM something. And data centers, we use data center received by terminal servers. We use this front-end processor for getting data, and we have a application processor for displaying and storing data. Okay, this is right now what we are doing. Your current transformer will convert. You know what current transformer application is. Higher current to lower current, it will convert. Voltage also same thing. Step down or step down the high voltage input to signal voltage. Next, transducers convert signals from one form to another form. RTUs is converting electrical signal to transmit data over communication channel, and signal conditioning circuit along with ADC used for conversions. Okay. Next, your communication channels. Okay. We use fiber optic communication also. We use this optical ground wire communication also. We use power line communication also. We can use very small aperture control also. Other forms such as radio wave, microwave, GSM, everything can be also used. Okay. But we are using this fiber optics, OPGW, PLC. These things we are using right now in our system. Okay. Okay. Again, same thing. Next, this control centers, we have front-end process. This front-end processor will just after through communication channel, you will connect to this front-end processor. They have application layer. They have a graphical user interface where you can users from our control centers will see that they have a network. We have a LAN system where we are connected with this, and we have access to it. There are for cyber security, they have a firewall with this system. We have a third-party audit for every 3 months. They will come here, they will check, and they will see whether someone has entered into the system or something like that. We have our user authentication and active directory service. Other software such as EMS also is available here. This is the thing where from RTU we will communicate to a subload dispatch center. From subload dispatch center server to SLDC. From SLDC to RLDC. From there to we are all monitored by NLDCs. Okay. This again some subload dispatch center to every SLDCs, whether it is AP or Karnataka. From there we have SLDCs, regional south regional load dispatch center, west, north, east, northeast, everything we are having. We have two things. They have NLDC main and NLDC backup. Suppose if the server is low in the main, they will go for backup. Okay. See, this is a line where we will use a CT and CVT same time. You have a transducer. It will give input to this. Again, RTs, FEP, front-end processors, SCADA, and graphic user interface. This is how the system components conversion rate happens. Okay. This is again hardware. This is the switched equipment, field equipment, where your PT and CT is there. Through that, you will connect to a transducer. Transducer again output will goes to our analog to digital converter from your RS 232 port communication protocol. Something they will use, anything they will use. But this is the overall hardware connectivity for SCADA at substation level. You can see this again. See, from circuit breaker also we will whether we will get this analog digital data, how whether it is on or off position, everything we will monitor in our SCADA system. Okay. This is field level. Through communication systems in through FEP we will acquire the data, and this data in real will be saved in a real-time server. Will be the historic data will be application layers will be there. Here we will work as a operator in workstations. Okay. In real time your system we will be our SCADA system will show a display like this. Okay, where suppose this is the generation stations. You can see this is all your buses. This is your 400 kV bus, and this is our switches, and you will see breakers here. Okay, this will be you can see a breaker here. See this graph, this values of analog values and your digital values. Everything, whether it is on off or your analog value in the field level will be seen by our LD centers in control centers. You can watch this screen like this. Okay. We have a SCADA subsystem also. In SCADA subsystem, you will have this storage and display equipments also. Okay. Next, this is for first I showed you for monitoring what we are doing. Next, for a contingency analysis, we have two things. For contingency, okay. Contingency is when a component of power system fails or changes state, such as transformer outage or the circuit breaker opening or tripping happens. Suppose any abnormalities happen, all your parameters will bend, all your power flow will change. So if it is within the limit, no problem. If it is not there, we have to analyze that. Okay. Contingency analysis helps to identify vulnerability and potential risks to the power system. It helps to ensure that the system can withstand unexpected equipment failures. It helps to develop proactive measures to protect the grid from disturbance. Okay. Okay. Your contingencies are two types. One is physical contingency. Suppose equipment fail, or like power line goes into outage, or your auto transformer goes into outage. They are physical equipment contingencies. Okay. Power flow does not recognize the geographical boundaries or asset ownership. Does not check the map to determine the shortest route. Flows are dictated purely by impedance of the transmission line, point of injection by generators, and point of consume by the loads. Okay. Okay. This ATCs or available transfer capacity is the remaining transfer capacity available for a new transaction after considering existing commitment and reliable margins. This ATC is equal to TTC minus RTC. This TTC means suppose if a transmission line is there, the total transfer capacity is the maximum power that can be reliably transferred across the network under normal operating condition for a transfer from a bus to bus. Okay. This ATC is the available transfer capacity. If you, if you total capacity minus reliable margin, you will get this available transfer capacity. This available transfer capacity, if there is some outages, there are some line goes into some problem, means that outage is declared in the line. This ATC should be monitored by us. Okay, the amount which can be transferred physically will be monitored by us, and this ATC will have some standard which is decided by RLDC. RLDC works out transfer, means that for interstate lines, like if it is from Karnataka to Tamil Nadu or west of Maharashtra, somewhere, any line. Okay, RLDC work out total transfer capacity and available transfer capacity of inter-regional link based on the low studies 3 months in advance. Normal and the first contingency scenario analyzed to determine the ATC and TTC of the inter-regional links. NLDC will combine the file from all the RLDC and declared in the website. You can see this, how much a line can transfer. Everything will be decided by RLDC through they will study the flow of power from where to where it is flowing. Then they will declare. See, above this load, it should not go. They will decide like that. Suppose if it is going like that, they will have a corrective action, which I will say later part. Okay. For calculation of TTC, ATC of inter-regional links, all line connecting two regions are considered irrespective of their ownership. Whom now private parties are also players in the market, right? Even if they are generating energy, they are also considered. Not only government parties are considered, government PSUs are, everyone is considered now. See, now subload dispatch center is working as an autonomous body where everyone is equal for them, and everyone can inject, anyone can transmit energy through the grid. Okay. Then this is for physical. For electrical parameter contingency like frequency, voltage, etc., we have this grid codes, Indian electric grid codes, where our frequency should be minimum of 49.5 to 50.3. Okay, we have standards. Suppose if it is going below this contingency of 49.5, we have to go for load shed, or we have to go, some corrective action has to be taken. Okay, this is for standard for our frequency. This is standard for our voltage. You can see this. See, bus voltage should be maintained in every bus. Suppose if it is a 400 kV bus, it can be plus or minus 5%. Okay, this is a standard. Where our IEGC is following. And if in 230 to the 220 volt kV system, you have a 10% clearance. It means that you can operate from 445 to 198. Anything is okay. If it is going below 198, again you have to take action. That is the job of a grid operator. We should not make the system to go below or above the permissible limit, or that is what we have to analyze and we have to decide. Okay. Next, suppose if it is going beyond that, what we have to do? We have to take some corrective actions for that. Okay. That is where our grid security comes. Okay. Suppose we are not correcting, automatically our grid will collapse. Okay. Suppose your generation is not matching with your, your demand is not, generation is not matching with the demand, or what will happen? Demand will go on rising, and you will lose out of synchronization, and your grid will collapse. Okay. For that, we have this 5 schemes we are having right now. ADMS is automatic demand management system. We have under voltage systems. We have DF by DT system. We have a special protection scheme systems, and we have islanding schemes. Okay. See, just an analogy for what these are. Okay. ADM is nothing but if you have a fever, we will take some medicines. First day we will take some paracetamol. We will have some medicines. Okay. Suppose if the fever is prolonging for 1 day, we will go for an antibiotic. Something like an antibiotic which we know, whatever we have been used to, we will take that. This df by dt is like going to doctor and just having a syringe, something kind of thing. And this special protection and islanding schemes are like going and admitting in hospital. Okay, just an analogy. You just have the you just will go next. This the following logic has been finalized for implementing ADMS implementation. See, already we have seen the contingency. Your grid frequency should be within 49.5 to 50.3. That is a standard thing. But even before that, we are securing the system. If the frequency is if the frequency is below 49.85 itself, or your over dial, which I said earlier, your dial of the grid means that your load is more than what your generation by 250 megawatt. This is subjected to only our state. Okay, suppose your frequency is below 49.85 and your over dial is above 250 for more than 15 minutes, you have to initiate stage 1 tripping. And this stage 1 tripping is for Tamil Nadu only. This means that it is for our grid only. In that, your expected relief should be 200 megawatt. Means that if a frequency is 49.85 and your trial is more than 250, you have to give a relief of 200 megawatt. Okay, this is secondly, after 10 minutes, you will trip. Suppose this happens and you are going into tripping. Okay, you are shedding some loads. Okay, after 10 minutes, even if the frequency is not improved and if the same condition prevails, you will go for stage 2 tripping. Okay, stage 2 tripping, again you have to give a 200 megawatt of relief. Okay, again after 10 minutes, if the frequency again prevails the same, again you have to go for stage 3 tripping, which would again be triggered. Automatically it will happen. Okay, for example, see, this is how our SCADA system will look like, where we have this automatic demand management system display, where we have in Tamil Nadu we have 3 load dispatch center. One is in Erode, next is in Chennai, and we have one in Madurai. Okay, these are the feeders. Okay, so you can see here in Madurai load dispatch center we have group 1 tripping, where our frequency, if it is below 49.85 and your over dial is more than 250 megawatt, for 10 minutes they will see. Again that they will initiate first tripping. If again the condition is prevailing in that way itself, again it will go for group 2 tripping. This group 2 tripping, it will go for group 2. Again, if it is prevailing, again it will go for group 3, so that you will get a relief for 600 megawatt. Okay, next. As I said, this is for ADMS implementation. Okay, first we have seen ADMS. Next, this under frequency implementation. This under the following logic has been finalized for under frequency implementation. Suppose we have already said that. Okay, suppose your frequency is below 49.5, you have to have some corrective actions. Okay, well before that itself we have taken action. Suppose if frequency is reducing drastically, if it is reaching 49.4 hertz, immediately it will trigger a signal 1. Stage 1 trip should be triggered, would be triggered, expecting a relief of 200 megawatt. Immediately it will trip. Even if your frequency is reducing and if it is reaching 49.2 hertz, then stage 2 trip would be triggered. If frequency is below 49, stage 3 will be triggered. In frequency is 49.8, again stage 4 will be triggered. Everything will be triggered immediately. Every tripping has a load relief of 200 megawatt, so that the system your frequency again goes near 50 hertz. Okay, this is how it will have under frequency relay tripping groups, where we have 4 groups in thing. You can see this. In every group we have set of feeders which we should trip, and this trip again, if you all every SLDCs we have our own group of feeders which have to be tripped for under frequency.
ஸ்லைட்ல கிளிக் பண்ணா வந்து அதே கட்டுறாரு.
Yeah, I didn't get you again. Hello. Yeah. Any doubts?
No, please continue.
See, previously I showed this ADMS, Automatic Demand Management System slide. This is where we had a set of feeders which it should be displayed. Where now I'm showing a under frequency trip. Where under frequency also we have a certain group of feeders which have to be tripped, so that you have to give a relief. Okay. Next we have df by dt. If your frequency is below 49.5 and same time your frequency is drastically changing, that time again stage 1 will be triggered, and stage 1 next, if your frequency is 49.3, suppose your frequency is immediately dropping to 49.3, immediately stage 1 stage 2 both will be triggered. It won't get delayed. In the same time, your if df by dt, your under frequency trip will also initiate. These all things will happen automatically. We have trip signals for that in SCADA, so that if it is reaching this permissible bit, automatically it will trigger the tripping. Okay. For df by dt, we have only two stages. One is 49.5 and 20.2, sorry, 0.2 hertz per second. If this is happening, automatically we have set of feeders where it will trip automatically and will give a relief for the network or the grid. Okay. This special protection scheme, the following logic has been finalized in the special protection, SPS is special protection scheme, where we suppose, for example, I would taken a line. It is a 765 line from Raichur to Solapur. It is a interstate feeder, where Raichur is in Karnataka and Solapur is in Maharashtra. It is 210 kilometer. Here you have more than 1000 megawatt transmission between these lines. So whenever this line is tripping, okay, if suppose this because of some outage or some external factors, immediately we will initiate a trip signal to feed us, so that the grid frequency is balanced. Okay. Again, our Kudangulam nuclear power plant, which is 200 megawatts. Okay, 2000 megawatt. If immediately if 2000 megawatts goes out of grid, again we will face some unbalance with the system. So that immediately we have to give relief to the system. So we immediately will trigger some trips, so that we will get a relief from the network. Okay. So you can see SPS scheme, Raichu Solapur trip signal 1. Means that we have certain feeders within this. That whenever our suppose this Raichu Solapur transmission line trips, immediately these following feeders will be tripped, so that it will give a immediate relief to the grid. Okay. Apart from this, we have islanding schemes. Islanding schemes is that, see, these have if our frequency is 49.5, see, if our frequency reaches 47.5, for 10 seconds it is prevailing in the stage. It will have a stage 1 tripping, where it will trip both generation as well as it will trip both load. Okay. For transmission network and generation, both will be tripped. If your frequency is below 47.5 and for 10 seconds, and or 47 hertz for 5 seconds, if it prevails also, it automatically will go for stage 1 tripping, stage 2 tripping. We have many feeders for this, because it will completely island a network. Means that it can even differentiate south and already now we are having one grid system. Now if this islanding till now after one grid we didn't face any islanding effect. Suppose this islanding is happening, our frequency is below 47.5 now, it will automatically even interconnecting, all your interconnecting networks will be first immediately tripped. Later again we have to restart. That is a black start operation. That is a different scheme. But immediately if it is below 47.5, it will start tripping. And your frequency, if it is going below above 15.5, immediately we have trips for your tripping your generation stations. Okay, so that you are generating more, but your demand is less. Now your frequency will shoot up. For that, again they have trippings for your generation station. Okay. For under islanding scheme, we have this df by dt also. Momentary, if it is per hertz, if it is your frequency is going below minus, dropping drastically, now again islanding will happen. Okay. these securities which we are having in the grid is as per grid code, sir. This all securities which we are having in the system is as per grid code, sir. This is applicable to everything which we are connecting with the common grid. Okay, if you are having a microgrid or you are having farming a community where you are operating your own energy which is self-sufficient for you to sustain the demand. Even if you connect this with the point of common coupling, what you will say is you are connecting with the grid. All these standards should be maintained. Okay, your frequency should be 49.5 only. It can be within 49.5 to 50.3. This is mandatory as per IEGC standards. Everything what I have discussed will be applicable for your microgrid if you are connecting with the main grid. Okay. Next. Okay. Current scenario, electric supply industry has encountered new challenges due to increasing demand. Every year we have a increase in 10% of our demand. Okay, and changing consumer expectation. Customers now require consistent quality of power supply, including minimum outage and stable voltage level, necessitating undergrading to aging infrastructures. Okay. Diverse energy resource in India. India is rich in both. We have every source: solar, wind, coal, oil, everything we have. The country energy portfolio includes coal, oil, natural gas, along with growing emphasis on renewable energy source to meet with the future energy need. Okay, this is the data which I took it from NLDC side. Right now, regional wise we are having. Now the capacity of installed is around 410 gigawatts we have installed. This is in 2022. Right now, I think it is 5.5 gigawatts. Sorry, 550 gigawatts it is. Next. In 2002, our all India maximum demand was 211 gigawatts. Okay. Right now, our Tamil Nadu demand, peak demand was 19,150. It was last year summer. Okay. This year we are expecting around 20,500. Every year there is a rise in 10% of demand. Even in consumption wise also, we have a demand of 5 to 6% in Tamil Nadu itself. National level, it will be like that only. South region, we have installed maximum demand of 60,876, out of which Tamil Nadu has 19,000. Andhra and Telangana is previously they were more than us. They had a demand of 27,000. Now, as it is separated, they are below us. In southern region, we have an installed capacity of 112 gigawatts. In all over India, this is what it is given. Then this is our consumption. Per day consumption, this is. Then, okay. Now our demands are, sorry. See, our demands are increasing by 10% every day. Okay, every year. Year by year, we are having a demand. How to meet that? There is a solution. The smart grid represents more than just a technical application. It is embodied a vision for transforming electrical industry. This vision includes advanced two-way communications. Two-way communication in sense powerful communication. Meanwhile, we have to communicate with the load till load base. Now we are communicating only with the grid. Okay, we never communicate with the consumers. Who is consuming, we never communicate. If this smart grid is adapted, we will communicate with the consumers directly, and it will be a two-way communication. From there also, we will receive. See, now at present, we don't know who's consuming, how much they are consuming in real time. You can see your energy meter. Every assessor will come. He will note your reading, and he will go and enter into the computer. You will get the bill. Right now, this is what happening. We never know how much we are consuming everything. End of the month, your assessor will say how much we are consuming. And in smart grid, it is not the case. You will have two-way communication. You will know how much you are consuming. Like through even mobiles, you can monitor everything. This is the technology we have to adapt in the future. The present integration of energy resource. Present scenario is like this. We will be generating somewhere, and we will through grid we are consuming this. We are taking loads. Okay, but in future it will be like this, where everywhere you will have solar grid, hydrogen storage, and everywhere you will have industries in that place. You will have your own generations, and everything will be integrated with the grid. Okay. See, current grid communication, we have only one way. Typically, not real time also. Okay. In grid, smart grid, you will have two way, and real time communication will be available. Okay. Interaction is limited. It will be, customer interaction will be limited. Here it will be extensive. Okay. So I think only for HT consumers we have made something that means that real time they can monitor. Okay. Metering, here combination of automatic and manual. Here we are using the digital enabled real time pricing meters. Operation, now it is manual equipment check and maintenance. If you see even now in power system, substations, there is operator. He will, for every 1 hour he will go, he will check the transformer, winding readings of oil temperature of the transformer, winding temperature. He will monitor for every hour. Even now it is happening like that only. He will go for a round. He will note everything. Even he will note in a log and he will manually enter it. Now we have a log system in computer. We will update in that. Okay. This is the remote monitoring. We will with the temperature or which is monitored from remotely for a transformer itself. We will check for oil everything. We will check DGA test everything, and remotely itself we can do. Okay, in smart grid. Generation is centralized. Here's centralized and distributed. Okay. Next, power flow limited. It is compression automated. Okay. Reliability prone to failure, cascade outage, and essential reactiveness. Here, automated proactive protections prevent outage before they start. Next, restoration following disturbance. Manual. This is it will heal itself. It means that it will automatically adjust the load and it will manage with the grid. See, this Synco phasor monitor, which we will say as PMUs, it is like a master checkup. Your PMUs are a master checkup. Where if you have an analogy, it is like a master checkup. You have RTUs. Anyway, RTUs through the line, they are communicating to us SCADAs. This PMU is like a master checkup, which is done for every second. You can do 48 master checkups. Like that, your entire grid will be subjected to scanning for every second. It will scan for 48 times. These PMU are implemented by National Load Dispatch Center. See, as it is very costly, they have not installed in every area. Selectively, they have installed. I think around 500 to 600 PMUs they have installed all over India. This PMU, what it will do, it will scan the entire system. It will scan they have installed in 400 networks. Okay, so it will scan the system for every second. Every second it will scan for 48 times, and it will give the power flow. How much dispatch is happening, everything will be monitored by NLDC through PMU. So, it has a clock signal, GPS based clock signal, where it will stamp time according to which it will, taking as a reference the geographical locations, it will easily compute how much the dispatch is happening. Okay, this is what we are in modern smart grid. We have to use this synchro phasor monitoring. Okay, deployment of phasor measurement unit. This will take deployment of phasor measurement unit is growing along with the development of predictive algorithm that can assess system risk. Okay, it will suppose some parameters is changing now. It will with the previous data, with the real time data and the past data, it can easily monitor, and it will it can easily assess the risk. Okay. For example, Center of Energy Advancement. Center of Energy advanced through the technology innovation initiated project for this, for directly input phasor data and an ultra fast load dispatch flow to identify the thermal overloads. Okay, voltage concern, voltage installation, everything they are doing there. Reliable broadband communication channels are needed to accommodate the wide development of this tool. Next, PMUs. This PMUs from the field level. PMUs again, it will go to data concentrator, which is again, it will be a PMU. This PMU will go to a master PMU where they have application programs where state estimators will find alarm if something dispatch is wrong. It will monitor. It can be integrated with SCADA also. It will be integrated with SCADA. You can see all the real-time data also, and if something goes wrong, it can protect immediately. It can give trip signals in field level, so that your system is prone to be protected from abnormalities. Okay. Next. This, for example, PMU will have a voltage and phasor data or current and phasor data. It will evaluate with the reference thing. If this is not with the safety thing, okay, if it is not within the limit, they will either go for load shedding. Load shedding they may adapt, or they will go for generation rise, or they will go for tap changing of the transformer to adjust the voltage, or they will go for reactive devices to just boost up the voltage. Anything can happen. Means that they will monitor the system by themselves. Still, this is in development stage. We can't. We are not using. See, right now in SLDCs, we are using only RTUs for integrating with the SCADA, for communicating with the SCADA. But this PMU is more useful than RTUs. Okay. This is what the PMU for synchronizing snapshots of relative rotor angles. Using GPS, they will give a timestamp so that at the same time they will calculate the load dispatch in every buses. So that with that they will come for load dispatch calculations. Okay. Your intelligent electronic device, remote terminal unit, RTUs for supervision data. SCADAs are similar, smaller and less expensive than before. For this reason, because of this cost, we are using SCADA RTUs and is expanding out for the transmission system to the distribution system. So, okay. Now we are forming this RAPDR project. The government is initiating this project. Through this project, what they are doing is that they are trying to implement this metering work in everywhere. Okay. What government is trying to do is they want to meter everywhere with the smart meters also. Now there is a pilot project in Chennai also, where in Tamil Nadu Electricity Board we have more than 60,000 consumers. I think we have installed a smart meter. These smart meters will just for real-time consumption readings. We have done that and it is successful. Only thing is that the cost is very high. We are waiting for schemes, whether central government scheme, anything, if it is approved, we will start our work. Smart meters, real-time or near real-time sensors and real-time pricing. Okay, power outage notifications, power quality monitoring, peak demand rates. These things can be monitored by smart meters. Okay. Again, we have our home automation and home area network. This allows homeowners to manage energy consumption, enhance security, and improve overall convenience. Okay. In the context of smart grids, HAN enables communication between utility companies, individual homes, facilitating real-time monitoring, control of energy usage. This bidirectional flow of information helps in optimizing energy distribution, reduce peak demand, and supports enable energy integration. Okay. HAN can also enable demand response program where application adjusts the energy usage based on the signals from the grid, contributing to the good stability and efficiency. This is what what I was saying. See this, if this home area automation, if supplier, consumer can interact, and if he knows to manage his load, it will be well, because grid will be, grid will not strain more. If it is a peak demand, automatically you can reduce your generation, consumption, so that grid is not, is in operating in a safe mode. Okay. See, today's scenario is like this: one-way communication from generation. Our line is going like this, and our consumers are here. They are using this right now. See, if in future, what it should be like this, where you have a renewable energy source in everywhere, smart meters will be installed everywhere. Every connections will be going to electric control centers where even future, who knows, it will be an AI generated AI model also, which will automatically do all things from generation to distribution till the consumer usage. It may operate and it may manage the grid well than us. Even our government right now, solar Surya Ghar scheme they have implemented. It is the first phase of this decentralizing thing. What happened is that first government initiated projects like Green Corridor. Okay, Green Corridor means they will pick a site where they have a high possibility of generation. They will set up a substation and they will suppose, for example, they have in Tamil Nadu we have chosen Kamudi. Okay, Kamudi where now the capacity of solar installed capacity is around 1,500 megawatts. Okay, capacity is around 1,500. Okay, installed capacity. Okay, they initiated project. They just form a green energy corridors where your generation will be near and your substation will be nearby. Through substation, they will pump to interstate lines. What happened is that it was what you will say weather forecast. If suppose you are generating 1,000 megawatts, sometimes if there is a passing cloud, you will you will feel a sudden decrease in the load. Okay, sudden decrease in the generation, so that grid will oscillate. Not to avoid this thing, we are trying to decentralize. Means that every home, if it is having a 3 megawatt or 2 megawatt, it will reduce the load of the grid, and again our energy will be decentralized, so that even during weather conditions like windy or cloudy conditions, a solar passing cloud will not be moving in the entire Tamil Nadu. Means that if it is in Theni, you will not get the clouds in Madurai. You can generate your energy over here. That is why we are now government is framing policies to decentralize the renewable energy also. In future, we can expect more renewable energy penetration into the system. As part of power system security is concerned, whatever grid code is applicable for now main grid, it will be applicable for your micro smart grid also. Okay, thank you. Any questions? Any questions?
Participants, please ask your any questions.